All right, class. So today we are moving on to triple integrals, right? So we already discussed double integrals, and because this class is kind of about expanding your mind, right? Like you can listen to the Joe Rogan Experience, or you can take vector calculus. And so when we were studying two-dimensional integrals, double integrals, we learned that the integral of a function over a two-dimensional region was like the volume, the signed volume rather, between the function and the region in the plane. Well, what's the next dimension higher version of volume? It's another word. It's not density. We don't have a word. There's not going to be a good word for it that you guys are going to know. Some might call it hypervolume. Yeah? Oh, yes. Yeah, sure. Yeah. Yeah, that's a good point. That's a good application of what we're going to be doing in this section. So, what was your name? Sorry? Moises? Yeah. Moises was talking about if a function has units of density, then that is a very good reason to want to integrate such a function over a three-dimensional region. So we'll get to that and other similar applications later, starting even perhaps by the end of today's lecture. But in analogy with thinking of double integrals as volumes, you could think of 3D integrals as hypervolumes or four-dimensional volumes or four volumes, if you will. And we started off double integrals by doing them over rectangles. So what should we start off doing triple integrals over? I heard cubes, or how about cubes whose sides can be maybe different lengths? I'll just call them boxes, okay? So that they will be a product of intervals. As such, I'll write it down in a second. First, let's suppose that we have some function. Now it's a function of three variables. So like Moises said, density would be an example. Temperature is another, where it depends on what point in space you are. So you could view temperature as a function of three variables. We'll suppose that f is a function of three variables, and that it is continuous on some box B, which is a product of intervals. How about AB, CD, and EH? Can't use F. So in R3, some box in R3, then the triple integral of f over B will be denoted, we use 3 integral signs. And there's actually a few different ways we can write it. So we might also write it as the triple integral over B. We might express the arguments of f. Or we might even write it as, instead of dv, we might say dx, dy, dz. There's actually even more ways it could potentially be written, but I'll try to keep things simple for now. And what does it equal? Well, just like in the two-dimensional case, it equaled an iterated integral. Well, same thing here. So it will equal an iterated integral, where let's say we do, how about z first? So the z integral, that went from e to h, and then we do the y interval from c to d, and the x integral from a to b. And whenever you see an iterated integral like this, you can imagine in your head that there are parentheses there, but we're not going to write them. And of course, as was the case before, there's nothing special about doing things in this order. We could have done, I don't know, y first instead of x, or z first. So we could have also written it as, how about, let me interchange y and x, in which case it would be c to d and a to b. Of, okay, that went z first, and then x, and then y. Or how about, let's switch the role of, how about z and x? So it could have gone c to d, e to h, a to b of x, y, z. So that was dx, dz, dy, etc. There's 6 total ways, or orders, and rather, that I could write this. I'm not going to write all 6. Let's do an example. How about if xyz is xy squared on 0, 1 cross 0, 2 cross 0, 3, which I will call b. So let me try to draw it first. Yep. Oh, you mean the intervals that I wrote for b? Yeah, correct, yes. It's always given in that order. Mm-hmm. Okay, so if I try to draw the region B here, look like there's 1, see maybe there's 2, and there's 3. Okay, cool. There's a nice box. So that is the volume B. And what does that integral come out to be? So according to our iterated integral formula, that would be 0 to 1, 0 to 2, 0 to 3 of xy squared dz dy dx. So, okay, that's 0 to 1, 0 to 2. There's no z dependence there, so I just get 3xy squared x y cubed over 3 from y equals 0 to 2. Cancel 3's. 2 cubed is 8. Cool. So I guess 4. Any questions? And wait, who was asking me about the intervals? What was your name again? So you were saying that like if you got, oh, sorry, I was kind of distracted. You were asking like if you got AB cross CD cross EF, could it ever be that this was Y and this was X or something? Well, what it will always mean is that the first interval is what you are considering your first coordinate. Okay, so since this interval is written first, that corresponds to whatever coordinate you continue to keep writing first. And by convention, we always call that x. So yeah, that's the short answer. That's the answer to your question. And I've super rare that you would ever see it any other way. Mm-hmm. Okay, so recall what we did for double integrals. After we did integrals over rectangles, we then generalized to elementary regions in the plane. Elementary regions were a more general shape than simply rectangles. They were shapes where instead of two parallel lines on the top and on the sides, it was a region where you had a function on the top and a function on the bottom, or possibly a function on the left and a function on the right. So now, and this is going to be a challenging part of the lecture for me to draw, we're going to generalize that to 3 dimensions. So what are the 3-dimensional analogs of elementary regions? These are going to be regions where once again, there's always one function on top and one function on the bottom. Or that's only if it's what we would call like a z-simple region. You could also have one function in front and one function in the back. Or maybe you might have one function on the left and one on the right. So let me try to encapsulate that. So one function is between two continuous functions of the other. Let me start over. One variable is constrained to lie between two continuous functions of the remaining two variables. The remaining two variables themselves are constrained to lie in a planar elementary region. Planar meaning region. A planar region is a region in the plane. So, for example, let's say D is an elementary region in the xy plane. And, ooh, what Greek letter is that? It looks like a nu. It's not supposed to be a nu. It's supposed to look, what's that one? That's a gamma. That's a, yeah, lowercase script gamma. So gamma 1 and gamma 2 are continuous functions on D such that one is less than or equal to the other. All right, so then the set of points in space such that x and y are in D, and z satisfies that it's between the two gammas. And that is an elementary region. Whew, there's a lot of writing. Okay, I better show you some pictures. So rather than try to draw these at this point myself, I actually just jacked some out of our textbook. So I'm just going to show you a couple of pictures from the book because it'll look neater than if I try to do it. So let me take this picture. All right, so I'm going to first do an example to show that the sphere is the ball, excuse me, is an elementary region. So consider the unit ball B, which is, hey, what's the difference between the unit ball and the unit sphere? Yeah, the ball is solid. The sphere is a two-dimensional surface. The sphere is the surface of the ball. Okay, so the unit ball is the set of x, y, z, such that x squared plus y squared plus z squared is less than or equal to 1. If it was equal, that would be the sphere. So I claim that this is an elementary region because at the boundary of the ball, which is where x squared plus y squared plus z squared equals 1, we have that z is equal to plus or minus the square root of 1 minus x squared minus y squared. Okay, so the plus and the minus correspond to the upper cap and the lower cap of that sphere. I was going to do a demonstration of this with an orange, but I forgot my knife. So I guess I'll avoid felonies today. All right. So here's the upper half. The plus corresponds to the top half of the sphere, which is like there, the upper surface, whilst the minus is the bottom half. Okay, so those are your two functions. That's like your your gamma 1 is the bottom, and your gamma 2 is the top. A bit trickier, though. What's your planar elementary region, though? So this is something you're going to have to do repeatedly when you're doing these problems. Once you figure out, okay, I figured out the function on top, I figured out the function on the bottom. Now, what's the planar elementary region that bounds the remaining two variables, which in this case are x and y? And in this picture, so x and y, maybe you can tell, are constrained to lie on the unit disk. That's the range of x and y values that are permitted. So that is the planar elementary region, something we've already studied. It's the set of x and y such that x squared plus y squared is less than or equal to 1. Now, let me give you the formula for integrating over an elementary region. So I'm going to need a picture here. In fact, so let me import another picture, which is this one. So let W be one of these regions. Let's use the region on the right. So sorry, on the left, excuse me. Let W be as shown here. Okay. And f be a continuous function on W. Then our formula for the integral of f over W will be, okay, let's see. So it's going to be iterated. It'll be 3 integrals. Which one do we do first? First, we do the one that's between the function of the other 2 variables, which in this case is the z integral. So the z integral, it's like you fix a point x and y, maybe somewhere in the domain. Z is going to start on one function and go up to the other function. It's going to start at gamma 1 of xy and go all the way up to gamma 2 of xy. Next, we need to do that, perform that operation for a range of y values. That range of y values for a given x will start at phi1 of x and go all the way to phi2 of x. And then finally, we need to perform all of this. Both of these steps already described need to happen for a range of x values from a to b. So that would be from all the x values from here up to here. Oh, crap, I made a typo. Oops, sorry. I didn't fill my differentials on the right first. The first one we did was z. The next direction we did was dy. The third direction we did was dx. Any questions on that one? Yes? Yeah, right. So this whole shape, good point. Yeah, this whole freaking block thing. Yeah, that's W. The whole thing, the solid shape. If we use, for example, the shape on the right, how would things change? Well, for one, does anyone notice a typo in the image on the right? I was just writing this lecture an hour ago, and I was like, wait, there's a typo in the book. Anyone see it? It says x is chi of x. Yeah, no, that's supposed to be x is a function of y. So let's fix that here. This should be there we go. Okay. Yeah. Okay, so if we're in that scenario, which is, so now this one, then what would our integral formula be? It would be triple integral over w of f dv is equal to, so, okay, so we're still doing z first. So it still goes from gamma 1 of xy to gamma 2 of xy, f of x, y, z, dz. But now, because our elementary planar region has x between two functions of y, then our second integration is with respect to x, and it goes from chi 1 of y to chi 2 of y, and then finally y, as you can see, goes from c to d. So from c to d. Any questions? Yes? Oh, please. Sorry? Okay, yeah, you can see, yeah, the difference is in the second scenario, D is an X simple region. In the first one, it's a Y simple region. So similarly, for the 4 other cases, right? So you're going to have 4 more cases, 2 more where you integrate X first, and 2 more where you integrate Y first. I'm not going to write them all down. Note that if f is equal to 1 on W, then what do we get for the integral? Integral over W of f dv is the integral over W of 1 dV is the volume of V. Sorry, the volume of W, excuse me. And we're going to denote this by V of W. So we can write this is equal to V of W. In fact, I introduced this for a reason because we can use it to talk about averages. So if we have some function f from W to R, it should be reminiscent of the 2-dimensional formula. You integrate f over the entire region, but then you divide by the, well, in this case, volume of the region. Okay. And let me introduce some notation here. When the context is clear, I'll just write f with a bar over it for the average of f. Right, so then this formula becomes the formula for f bar. Cool. Okay, so let's do an example. Let's let T be the following tetrahedron. Tetrahedron, by the way, is the same as a triangular pyramid. So how about okay, so there's T. let's find the volume of T. And then let's find the average height of a point in Z. The average height of a point in T. Yeah, so how high is this pyramid on average, where in the xy plane, the height is 0. The peak of the pyramid is up at height 1 on average. Like if you spent a lot of time hanging around inside this pyramid and you randomly went from this place to that, on average, what would your height be? So first, we're going to need to do part 1, which is the volume. So the volume of T is the triple integral, as we just saw, of the function 1. So, okay, we gotta do a bit of work here. So you always have some choice in these problems with how you want to set it up. I am going to set it up with z being between a function of x and y, like most of the formulas I've been writing. So I'm going to let this triangle here be the base D, right, which is in the xy plane, D is going to look like this triangle. And then I need to find an equation for this face. It's a plane, so I need the equation of that plane. Okay, so the top plane is what we were calling gamma 2 of xy. The bottom plane was gamma 1 of xy, and that's just where z is equal to 0. But what about the plane on top? How do we figure out the equation of that plane? This is something that you're supposed to do in like 20C, I think. So this is section 1.3. To find gamma 2 of xy, see section 1.3 on equations of planes. I know that since it's a plane, that it's equal to some linear combination of x and y. And then I can just plug in the points that are on it, such as 0, 1, 0, 0, 0, 1, and 1, 0, 0. If you plug in those 3 points, you get the equation that gamma 2 of x and y is 1 minus x minus y. So you can check, like if you plug in those 3 points, they lie on that plane. Okay, good. So we found what gamma 2 is. It's 1 minus x minus y. That's this face here. Then for D, this line, it's not hard to see, is the line y equals 1 minus x, which is the same as this line. So if you, for example, viewed the top of this as phi 2 of x equal 1 minus x, and the bottom of this region as phi 1 of x equals 0, then you see that x goes from 0 to 1, so D is the set of x, y such that 0 is less than x or less than 1, and 0 is less than y is less than 1 minus x, expressed as a simple region. Whew. Okay, I set up all my functions and bounds. Now it's kind of automatic. Okay, from here on out, it's just plug and chug. This is kind of the tough part, was setting it up. Okay, so now just plugging into the formula. Let's see. So the integral over t of 1 dv, it'll be triple integral. And we're doing z first, which goes from 0 to 1 minus x minus y. And then we're doing y, which goes from 0 to 1 minus x. And then we're doing x, which goes from 0 to 1. So this is pretty straightforward to evaluate. Here, I'll just do it really fast. I actually get 1 minus x squared over 2. So I'm going to do this kind of fast. You should check this on your own time if you can't follow along. Cool. Okay, so the volume of this shape is 1/6. Seems reasonable, right? It's less than the unit cube, which would have volume 1. So, all right. That concludes part 1. For part 2, we want to find the average height. And by height, I mean I'm thinking of the z direction as up, okay? So it's like I'm asking for what is the average z value on this shape. Judging from the silence from the audience, I'm guessing not everyone is super happy about this. Just, I want to point out, I'm trying to give you examples because sometimes I get feedback on my evals that I don't do a lot of examples. But then I want to tell that person, like, well, you haven't seen what it's like if I do the examples. Maybe it's not so fun. But anyway, so I'm trying to give examples. Hopefully, like it's good for you guys and you appreciate it. As I said, I'm going kind of fast on this because I want you to sort of go over it on your own time and figure out every little part of it. So to find the average height, we need the integral of z dv. Okay. Again, this is just straightforward plugging and chugging because we already know all the bounds. Does anyone have questions, though? You can ask questions. I think I'm actually going to finish on time, amazingly. Okay. So the bounds are 0 to 1 minus x minus y, 0 to 1 minus x, 0 to 1, z dz dy dx. So, okay, 0 to 1, 0 to 1 minus x, what's that? Z squared over 2 from z equals 0 to 1 minus x minus y. So 1/2, 0 to 1, 0 to 1 minus x, 1 minus x minus y squared, dy dx. Oh, wait, so, okay, that's going to be 1/2, 0 to 1, negative 1/3 of 1 minus x minus y cubed from y equals 0 to 1 minus x. So what's that? At 1 minus x, it's 0. At 0, it's 1 minus x cubed. That gives me... Oh, wait, did I drop a minus sign somewhere? Minus 6. Oh, wait. I just picked up a minus. So, sorry, let me show a little bit more detail on the last step. Okay, I get to cancel these minuses. So that's 1/6, the integral from 0 to 1, 1 minus x cubed dx. That's negative 1 over 24. This is 1 over 24. Okay. So that's the integral of z. Is that the average? Am I done? I got to divide by the total volume, too. So last step, so z bar is, and by the way, just a sort of a check to see like if we're getting in the right neighborhood, look at this shape. On average, should the height of this tetrahedron, well, it can't be any taller than the top, which is 1, or any less than the bottom, which is at 0. So it's some number between 0 and 1. Is there more weight of this shape towards the ground or towards the peak? It's ground heavy. Yeah, it would be, we bottom heavy, we might say. So we're going to expect a number like not just between 0 and 1, but it should be like less than 1/2. Let's see just how much less than 1/2. We get 1 over 24 divided by 1/6, which was the average, giving us 1/4 is the average height of the pyramid. And that was like one of the problems that my 20E students hated on the final